Hello everyone. On this video we will see how you can use derivatives to find velocity and acceleration. Alright, so starting off, you should know that f of t is just your basic function. So it could be f of t, f of x, usually f of t when you're talking about velocity or acceleration, but your independent variable could be anything. Okay, so f of t, that represents your position at a time. Okay, so f of t represents an object's position at time that we will call t equals whatever. Okay, so since it represents the position at a certain time, it only makes sense that f of t is called the position function. Okay, now it doesn't have to be f of t, it could be g of t, it could be h of t, it could be p of t, it could be anything at all. F is just the variable that was chosen. It can literally be any variable. Okay, so don't get too stuck on the f for the position function because it can change. Alright. Now we know that the derivative is the rate of change. Okay, so we also know that the rate of change of the position function of the object is given by the derivative of the position function, which is f prime of t. Okay, now since we're looking at the rate of change of the position function, that means our f prime of t, which can be denoted as the velocity function v of t. So that's your velocity function. Okay, so you might see it as find v of t, you might see it as find f prime of t, depends on the question. Okay, so once again, it's more about concept than memorizing. Okay? Now, rates of change, just as a quick reminder, they are measured in units. For example, if you have miles per hour, or if you have meters per second, and et cetera, and so on. Okay, now the velocity does have a directional component to it. Okay, so moving direction kind of matters with velocity. So moving 10 miles per hour northeast is different from 10 miles per hour southeast. Okay, so it's not always seen as being the same thing just because they have the same rate. Okay, so velocity has a directional component. Since moving, let me move this up some, at a rate of 10 miles per hour northeast is not equal to a rate of 10 miles per hour southeast. Okay. Now, there is a way to use velocity where the rates will be equal, and that's where you come across your speed. Because if you're looking at your speed, it's a little different than velocity. Because with velocity, 10 miles per hour northeast and 10 miles per hour southeast are different. But with speed, 10 miles per hour is just 10 miles per hour. It doesn't matter which direction you're going. Okay? Now, to find the speed, you just take the absolute value of the velocity. Okay, so let me go and make a quick note there. When direction is not important, then the absolute value of the velocity, which sometimes is called magnitude, gives us the absolute value of your velocity is equal to the absolute value. Actually, I should move this down some, give it a little bit of space. All right, just so it's not all crammed up there. Okay, so the absolute value of the velocity function equals the absolute value of the first derivative of the position function. And that's what we call our speed function. All right. So if you are still writing, feel free to press pause, but we're running out of space on this page. I'm going to continue on the next page. Excuse me. Okay, so we know that the velocity is the rate of change of the position of an object. Now, what if we start to look at the rate of change of the velocity now? Okay, that's when we get into acceleration. Okay, so acceleration is the rate of change of an object's velocity. Of an object's velocity over a time that we will call t. Okay, so for example, let's say, I'm sure you've all seen the commercials where they say this car goes from 0 to 60 in 4.5 seconds. That's basically your acceleration. It's showing the rate of change of the velocity. So a car going from 0 miles per hour to 60 miles per hour shows a change in velocity. So we say it's accelerating. All right, so this is a quick recap. You have a function f of t. That's your position function. If you have f prime of t, that is also known as your v of t, your velocity with respect to time, or your velocity function. And your second derivative, that is now known as your acceleration with respect to t, or your acceleration function. Okay, so basically these two are the recaps. And this is the new explanation of the acceleration function. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our first example. Okay. So what if we have a ball and it is dropped from a height of 64 feet? Okay, so its height above ground, also represented in feet, after t seconds is given by the position function p of t is equal to negative 16 t squared plus 64. Okay. Now notice it says position function here. You may have questions where it doesn't say actual position function. It may just say is given by and then just give you that. Okay, so don't always look for it to say position function because it won't always say it, but know that this, your function, is called your position function. Alright, so for problem A, we want to find the velocity and acceleration functions. And for problem B, we want to find out what is the instantaneous velocity when the ball hits the ground. Alright, so let's go ahead and start with solving problem A. Okay, so we know we have our position function. So P of t is equal to negative 16 t squared plus 64. Okay, our position function. Okay. Now if we find the first derivative of that, our velocity function is the first derivative, which is equal to negative 16 t squared. So the derivative of that, so we have negative 16 times derivative of t squared, which is t to the 2 minus 1, plus the derivative of 64 is derivative of a constant is just 0. So that means your velocity function is equal to negative 16 times 2 is negative 32 t to the 2 minus 1 is just t. So this is your velocity function. Okay, so to find our acceleration function, we just take the derivative of our velocity function. So our acceleration function is just the derivative of our velocity function. It's the derivative of negative 32t is just negative 32. Okay, so our acceleration function is negative 32. And I'll go ahead and mark that. Acceleration function. Alright, so now go ahead and solve for B. What's the instantaneous velocity when the ball hits the ground? Okay, so we know that when the ball hits the ground, what does that tell us? That the height is 0. Okay, so when the ball hits the ground, the height equals 0. Okay, because remember, it's dropped going up here a little bit. It's dropped from a certain height. It didn't start on the ground. So we want to know how long does it take before it hits the ground, or until the height is 0. Okay? So when the height is equal to 0, that means our position function, because remember, the height is given by the position function. That means P of t is equal to 0. So since our P of t is negative 64t squared plus 64, that means we want to find where negative 16t squared plus 64 equals 0. So if we add negative 16, well, if we add 16t squared to both sides, we end up with 16t squared equals 64. Because remember, we just added to both sides, and we have 64 equals 16t squared. I just flipped it around. Let me clean that up a little bit. All right. So if we divide both sides by 16, we end up with t squared equals 4. Square root both sides, we have t equals positive or negative 2. And since time cannot be negative, it just gives us t equal 2. Hits the ground after 2 seconds. Okay, now that tells us how long it takes to hit the ground. It doesn't tell us the instantaneous velocity when it hits the ground. Okay, so to find the velocity when it hits the ground, equals negative 32t. That's our velocity function. So that means to find the velocity after 2 seconds, v of 2, which is negative 32 times 2, equals negative 64 feet per second. Okay, so that's the velocity when it hits the ground. The instant it hits the ground, that's its velocity. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Excuse me. Alright, so let's say a ball is tossed into the air. Okay, its height above the ground, and this time we're going to measure it in meters, is given by the position function P of t is equal to negative 4.9 t squared plus 6t plus 2. Okay? And again, remember, they won't always say this is the position function. Most problems will just say is given by, and then kind of not tell you that part and just give you this. So be on the lookout for that. Okay? So we want to know what is the acceleration at time t equals 0. Alright, so let's go ahead and solve this one. Okay, now since we're looking for the acceleration, we're going to use the acceleration function, which we know is the second derivative of the position function. And there we go. Right, so we know that our position function is negative 4.9 t squared plus 6t plus 2. All right, and we know that our velocity function is the derivative of your position function, which is negative 4.9 times the derivative of t squared, which is 2t, plus the derivative of 6t, which is 6. And derivative of 2 is just 0. Derivative of a constant, always 0. So that means your velocity function is equal to negative 9.8, negative 4.9 times 2, t plus 6. That's our velocity function. But we're not looking for the velocity function, we're looking for the acceleration function. So we have to find the derivative of our velocity function. Okay. So it's the second derivative of your position function, or the first derivative of your velocity function. However way, they're all the same thing. Okay, so to find our velocity function, our acceleration function, excuse me, that's negative 9.8, which is the derivative of t is just 1, so that just leaves us negative 9.8, and the derivative of 6 is just 0, so our our acceleration function is negative 9.8. Okay, so this is our acceleration function. Alright, now at t equals 0, I'll go ahead and use the actual acceleration function at 0 equals, there's no t to replace with 0, so it's just negative 9.8. And for the acceleration function, it's meters per second squared. All right, so notice for velocity would be meters per second. For acceleration, meters per second squared. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, and this is showing the movement of a particle. Okay, so what do we know? We know that velocity tells us basically speed and direction. Okay, so think about a particle moving along a number line. So it's just going left and right. So consider a particle moving along a number line. Okay, so of course on a number line you have 0, then you have your positive values, and you have your negative values. Okay, so of course your positive velocity would be moving right, and your negative velocity would be moving left. Okay, now I just wanted to point this out before we start our next example, because this will kind of determine certain movements of the particle. All right, so if you're writing, feel free to press pause, but we're going to go ahead and start on that example. Okay, so for example, the position of a particle moves along a coordinated axis yeah, let's say, not that, I'm trying to think of the best way to word this one. That should probably be moving. Okay, that's where I messed up. Moving along a coordinated axis is given by P of t is equal to t to the third minus 9t squared plus 24t plus 4, assuming that t is greater than or equal to 0. Okay, so this one has 4 parts. Okay, part A, find your velocity function. Okay, so part B, what time is the particle at rest. Okay, so C, on what intervals is the particle moving left to right and right to left? Okay, the little thing we looked over before we started this one, I'm just going to cover this up for a second. That part, that mainly goes for part C. So that's why I went over that beforehand. And for part D of the question, we're going to actually sketch the path of the particle along a coordinated axis. All right, so we're going to go ahead and start with part A. Okay, which if you want, you can go ahead and press pause and do part A on your own. Okay, so we know find v of t. We know v of t, that's the velocity function. That's just the derivative of the position function. Okay, so the derivative of t to the third power is 3t squared minus the derivative of 9t squared. We bring down the 2, so we have 18 minus 18t. Derivative of 24t is just 24 times the derivative of t, which is 24. Well, so the derivative of t is 1, which gives us 24. And the derivative of constant is 0, so that's just, that plus 4 disappears. Okay, so now we look at B. Okay, we have to find the interval, not the time where the particle is at rest. Okay, now when you see at rest, that's the exact same as looking for when the velocity equals 0. Okay, so since we're looking for the velocity to equal 0, and this is our velocity function, we're looking for v of t equal 0. Or 3t squared minus 18t plus 24 equals 0. All right, so if we divide each term by 3, that actually simplifies that quite a bit, which is t squared minus 6t plus 8 equals 0. All right, so if we go ahead and factor this out, we end up with t minus 4, t minus 2 equals 0. Okay, so if we have t minus 4 equals 0 and t minus 2 equals 0, that means we have t equals 4 and t equals 2. Okay, so these are the two moments when the particle is at rest. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and continue this on the next page. Now set that there. Alright, so I'm just going to write down our velocity function. So instead of 3t squared minus 18t plus 24, I'm going to factor out the 3. So our velocity function is 3 times t minus 2 times t minus 4. Okay, so all I did really was take 3t squared minus 18t plus 24, then make that 3 times t squared minus 6t plus 8, and then went ahead and factored that part. Okay, so in case you're wondering, where did you get that from? That's all I did, just to kind of simplify it a little bit. So it's 3 times t minus 2, t minus 4. You'll see why I'm doing this coming up. Okay, so now we want to know on what intervals is the particle moving left to right and right to left. Okay, so left to right, remember, that's going positive, in the positive direction. So left to right, your velocity will be positive. Right to left, means that your velocity is going to be negative. Okay, so now what we're going to do is we're going to just draw out a little number line to help us visualize these things. So because remember, it's just a coordinated axis. It's just a fancy way to say number line. All right. So we know it equals 0 at t equals 2 and t equals 4. So let's say this is our t equals 2, and this is our t equals 4. Okay, so we know from here, and we know that t is greater than or equal to 0, so we can't say this goes on forever. This actually just goes from 0. Okay, so we have the interval here, kind of separate those, from 0 to 2. Okay, since it can actually equal 0. And this here is from t equals 2 to 4. And this is from 4 to infinity, since we don't know how far it goes. Oh, it doesn't equal 2. Let me clean that up just a little bit. Okay, so I changed it from the bracket to the parentheses, because remember, it can't equal 2. Because if t is equal to 2, then you have velocity of 0. We're just looking for whether or not in these intervals the velocity is left to right, positive, or right to left, negative. Okay, so if it's positive, it's going this way. If it's negative velocity, it's going that way. All right, so how do we figure that out? Well, we just kind of help separate this. We pick a test value. All right, so in this interval here, we'll go ahead and pick t equals 0 because it's just easier. Okay, pick t equals 0. Now you could have picked t equals 1, t equals 0.5, anything between 0 and not equaling 2. You could have picked 1.99999 if you wanted to. I just picked 0 because it's the easiest way to get the solution. Okay, keep it simple, or keep it simply simple. All right, so we plug it into, and this is why I rewrote our velocity function this way. Okay, so v of t, if we plug in t equals 0, we have 3 times 0 minus 2 times 0 minus 4, which is 3 times negative 2 times negative 4. Okay, so we don't really have to solve it. We just have to find out whether it's positive or if it's negative. This is positive. Okay, so since we know it's positive, what does that tell us? That the velocity is greater than 0 on this interval. Okay, so now we do the same thing here. Between 2 and 4. Again, you can pick 2.1. It can't equal 2 and it can't equal 4 because you'll just get 0. You can pick 2.1, 2.5. Just keep it simple and pick 3. Pick t equals 3. Excuse me. All right, so we go ahead and plug it into there. So we have 3 times 3 minus 2 times 3 minus 4. Okay, so that's 3. 3 minus 2 is 1. 3 minus 4 is negative 1. So we already know this is going to be negative. And if it's negative, then your velocity function is less than 0. Okay, same thing here. From 4, any number bigger than 4, all the way to infinity, keep it simple and pick t equals 5. Okay, so we have 3 times 5 minus 2 times 5 minus 4, which is just 3 times 1, which is positive. We'll give you a positive number. Okay, so since it's positive, we know that our velocity function is greater than 0. Okay, so now that we have that figured out, we can answer this by showing that the particle goes from left to right when the velocity is greater than 0. So it goes left to right on the interval from 0 to infinity. I mean 0 to infinity, 0 to 2. Or from the interval from 4 to infinity. Okay, and our particle goes from right to left on the interval from 2 to 4. T equals 2 to 4 seconds. And remember, that's your velocity is less than 0. All right. So we're going to go ahead and solve part D, which just going to have us sketch it. Okay, so let me do it. Actually, I'm running out of space. I want to make sure I'm not trying to cram it, so I'm just going to continue this on the next page. Okay, so if you're still writing, feel free to press pause. But I'm going to go ahead and continue this on the next page. Okay, so part D. All right, so now we're just going to go ahead and sketch the path of the particle along that coordinated axis. Okay, so to sketch the graph, we need our points where the velocity is 0, but but we know that the time is greater than 0. So what we're going to do is we're going to start at t equals 0. Okay, so starting at t equals 0, we know that our position function at 0 is going to equal just to kind of p of t is equal to t to the third minus 9t squared plus 24t plus 4. Just a little reminder. So p of 0, of course, that's 0 to the third power minus 9 times 0 squared plus 24 times 0 plus 4. So our position at 0 is equal to 4. Okay, so we know the velocity where it's equal to 0, so we know where we're starting. Now we're going to go to where our velocity is equal to 0. Okay, because remember, when our velocity is 0, that's when we've stopped. Okay, so we want to find out where we stop. Okay, so we know it's at t equals 2 and t equals 4. Okay, so at t equals 2, our position at that time is equal to 2 to the third power minus 9 times 2 squared plus 24 times 2 plus 4. Okay, so we know that our position at t equals 2 is 24. We're going to need those. I'm going to kind of highlight that. Okay, so now we know at t equals 4, move this up a little bit, we know our position at that time is equal to 4 to the third minus 9 times 4 squared plus 24 times 4 plus 4. Okay, so if we go ahead and calculate that, we end up with our position at t equals 4 is equal to 20. All right, so now we go down a little bit more and we draw our trusty number line. Okay, so we're going to go ahead and, since I'm kind of limited on space, I'm just going to go ahead and count by 4. So we have -4, 0, 4, 8, 12, 16, 20, 24, 28. That should be good enough. Okay, so now we know all the points where our time is equal to 0. Remember, our velocity is equal to, not time is equal to, our velocity is equal to 0 at t equals 2 and t equals 4. These are all your values of t. Okay, so t equals 0, well, you were just starting, so we're going to start there. At t equals 2, we know it's going to stop. So when t equals, oh, actually, should have moved that over the 4. It should be over the 4. This is your t equals 0. Sorry about that. Now when t is equal to 2, it's 24. So over 24, that's your t equals 2. Oh, actually, I should erase that. There we go. That's actually your position. So never mind that t. And when time is equal to 4, it's 20. So I'll put that just above the 20, where t is equal to 4. Okay, now this is where, going back to our previous page. Bring that back up. So I'm going to cover this up for a second. We see the intervals that is going left to right and right to left. Okay? So if you notice on that page, you're going right to left between 0 and 2 and 4 to infinity. So from 0 to 2, you're going right to left. Okay, so we might as well draw a little arrow there. Okay, but we're going from, we'll do the 4 to infinity in a second. But from 2 to 4 is going right to left. So let's get our particle turned around. So let me move this on the other side so it's not in the way. G equals 4. Okay, so it's going left to right from 2 to 4. And again, just draw the arrow going that way. Okay, so we see now that from 4 to infinity, it's going left to right. So that particle goes there, then turns around, goes that way from 4 to infinity. Okay, so this is the sketch of the movement of our particle. All right, so we'll move this over a little bit. Okay, so hopefully this made sense, and I will see you on the next video.